All right. Hello, everybody. Welcome to the September 2024 edition of VAST. This is the Virtual Astronomy Software Talks. That happens every month, the third Wednesday of every month. And we have two speakers. The usual procedures, we have two speakers that give about 20-minute talks each, and then we have 20 minutes after that for open discussion. If you have questions during the talks, feel free to put them in the chat or hold them to the end. And usually after each speaker talks, we'll have one or two questions. And then in the open discussion section, we'll get to as many remaining questions as we can. And just before we start today, I want to, me and the other organizers would like to highlight that this year the AstroPi collaboration has won the Lancelot M. Berkeley Prize. It's a trust prize for meritorious work in astronomy. And I think this is the first time that a software has won this award, which is pretty exciting, and just emphasizes that the work that we're doing is important. And so yeah, that was good news, and happy to hear that. So today, like I said, we have two speakers. Where did my list go? I had a list. Yes, so first we'll have Evan Schneider, a professor from the University of Pittsburgh. We'll talk about Cholla, a hydrocode. And then we'll have Ben Wibking, who's a postdoc at Michigan State, I think. And he will be talking about, I had it written down.
Quokka.
Quokka, that's right. Yeah, it's hard to pronounce. Okay, so yeah, I think we'll have Evan go first, if that's okay. And so yeah, I guess just take it away.
Well, yeah, so thank you for having me. Yeah, both Ben and I coming in with codes that have difficult to pronounce names. But yeah, so I'll go ahead and share my screen so you guys can see the slides. Okay. This 2 seconds. Okay, cool. You guys can see that?
I cannot see that.
No, not yet.
Oh,
Nope.
sorry. Hang on. It came up in the window, but didn't actually connect. There we go. Is that better?
Yeah.
That's better.
Okay, great. Right. So Michael asked me if I'd be willing to talk a little bit about my code, which is pronounced Cholla. And the rationale being that this is going to be a session, I guess, on GPU programming. So just to give a little bit of background, Cholla is a code that I started developing during my PhD thesis at Arizona. So the name is sort of geographically relevant. Cholla is a type of cactus, but it's also an acronym. So it stands for Computational Hydrodynamics on Parallel Architectures. And one of the things that I was trying to think about when I started thinking about what to talk about here, Michael had asked about, if we could talk about our sort of experiences porting to GPUs. And it's worth saying that one of the things I think that makes Cholla a little different than many of the codes that were sort of being developed at the time is that we didn't actually port anything, in the sense that Cholla is a GPU native code. It was written, we started writing it in part because people started, adding GPUs, accelerators to supercomputers, and it became clear that it would be useful to have codes in astrophysics that could run on them. So I thought I would start by giving maybe just a broad level overview about sort of GPUs and parallel computing in general, and then I'll talk a little bit more specifically about Cholla. So at the risk of telling you all some things that you already know, I wanted to make sure we're all sort of on the same page. So I've written here, Cholla is a GPU native massively parallel finite volume hydrodynamics code developed for astrophysical simulations. All of our development is done in the open, so you can find Cholla on GitHub. The development branch has the sort of latest updates. And I wanted to start by just saying, GPU native in the sense that, as I said, we actually, started from day one writing a code that was intended to run on GPUs. And that was because, as I think many people are aware, right, computer architectures have changed a lot in the last 20 years. And we are no longer in the era of sort of CPUs with a few powerful cores being dominant. Right now, we live in the era of extremely parallel processing. So graphics processing units, of course, were originally developed to do graphics processing, rendering pixels on screens. Now they're extremely common in HPC applications as well. And the idea was just basically, to devote way more of the transistors on your chip to data processing. So a typical GPU these days now has thousands of individual cores, each of which are much less powerful than the cores on a CPU, but when working in tandem, they provide a lot more potential compute ability. And so I just have a little schematic of what a typical GPU layout looks like in terms of the hardware. Those cores are then split into groups on these individual sort of multiprocessors, to use sort of NVIDIA's language. And those multiprocessors have their own sort of control logic and memory spaces, et cetera. And they are the things that are going to be basically in charge of deciding what gets computed and where. Right. So GPUs are really ideal for algorithms that follow a sort of single program, multiple data model. So if you have a lot of work to do in parallel, right, on your sort of problem, that's what GPUs are good for. And hydrodynamics is an example of that kind of problem. So I said, GPU native and massively parallel. What do we mean by massively parallel? Well, in addition to the fact that GPUs, right, are extremely parallelized, we also sort of designed from the beginning Cholla to be a GPU code that would run on supercomputers, right? So, as you may be aware, supercomputers, right, they're always chasing the sort of next peak speed. So this is just a plot I made of the sort of supercomputers that have been at the top of the top 500 list, which ranks the fastest computers in the world if people submit their benchmarks every 6 months. And the peak speed is on the y-axis in teraflops. So the dashed line at the top is 10 to the 18 flops, or exascale, a barrier that was broken by Frontier last year or 2 years ago, I guess at this point. At Oak Ridge National Lab. And I show this in part because, it's worth saying, on the supercomputer front too, of course, this speed gain is achieved by parallelism, right? Many, many thousands of nodes now, each of which is extremely powerful, working in tandem in order to get you these kinds of speeds. And, so far, this has been following a sort of Moore's Law-esque rise with a 15-month doubling time. I think that's actually going to turn over in the near future because we're reaching the point where actually things like interconnect speeds, data storage, that kind of stuff are now starting to be the bottlenecks for code as opposed to the actual speed of the computers. But of course, breaking exascale was an achievement that the labs were really interested in. And I also just wanted to note, the fastest of these computers these days, basically everything on the top 10 of this top 500 list are powered by GPUs. So, if we want to get the sort of most bang for our buck with our codes, it makes sense to run things on GPUs. So I mentioned that Cholla is a finite volume hydrodynamics code. So I just wanted to, again, make sure we're all kind of on the same page in case you haven't been thinking about hydrodynamics codes lately. So the idea there is just, when we run our simulation, we divide our domain up into individual discrete cells, right, or finite volumes. And the main work of the code is, we're given at some time the values of the conserved fluid quantities in each cell, right, the average values of here I'm writing it out as U, right, the density, the momentum, the energy, et cetera. And the work of the code is to basically calculate fluxes of those quantities across cell interfaces, right? And then you can use those fluxes in a time step update like the one that I'm showing on the bottom right, to then evolve the fluid forward in time. And so this is an inherently parallelizable problem because each cell, in order to evolve the fluid, only cares about local quantities, right? So this made it a really good test problem for sort of running on a GPU architecture, because one key with GPUs, right, is that things have to be sort of running synchronously, or at least have the ability to be running in parallel in order for the algorithms to be efficient. So how do we actually do that in Cholla? The mapping we use is pretty simple. So in GPU programming, you have this idea that the GPU can be, assigned a function that will then run in parallel on, as many threads as you like, basically. So millions of threads. And so it's worth saying a thread is a programming abstraction, right? It doesn't actually correspond to one of those individual cores, right? The GPUs only, have thousands of cores, but you can run with millions of threads. And the idea, again, is that those streaming multiprocessors are responsible for deciding, which calculation for this thread is going to run on which core and when, right? And they're very good at that. And the nice thing about this abstraction is that we basically haven't had to change anything about the fundamental structure of the code in terms of this sort of thread mapping since we wrote it, started writing it in 2013. Even as the GPUs add more cores, etc. This mapping is done by the processing unit itself, so we don't have to worry about it. So we basically do the simplest thing possible and just assign individual threads to individual cells. And then assume that they're gonna sort of run in parallel throughout the course of the algorithm. So just to give you a sense of what that actually looks like, right? If you were to run, the conserved variable update, right, in a C code, right, you would need to loop through all the cells. That's the sort of classic idea of serial programming. CPU is very good at this. They have high clock speeds, so they can go through many cells quickly, right? And so just to give you a little sense of what that function might look like, right? For, I to nx, where nx is the number of cells that you have, just assuming this is a 1D update for simplicity, right? You then are just going to go through and update each of these conserved quantities using the fluxes that presumably you've calculated at an earlier step in the algorithm, right? And one of the reasons I show this is because the GPU version of this doesn't look very different, right? In other words, this is what the CPU version looks like, right? A C version of this update. This is what the same update function looks like in CUDA, which, as I'll explain in a couple slides, is the GPU programming language that we use. Again, you just have some function on the GPU. The functions are referred to as kernels. And you give that function, the pointers to your arrays. Again, we're going to assume that you've already calculated the fluxes in some other kernel, right? And really the only difference here between the CPU version of this and the GPU version is that you need to know sort of where you are on this GPU grid, right? The kind of conceptual mapping. So you get what's called a thread ID, right? That tells you where you are globally. It tells you, what cell to update, right? And then, you have this sort of funny if statement that basically says, only update my cell if my thread corresponds to a real cell in the grid. So you can launch more threads than you actually have cells, and the GPU doesn't really care. So otherwise, the sort of functionality inside the kernel is very similar. And again, I partly show this because sometimes people are somewhat wary about GPU programming, but it's, on the C++ level, it's not very different than a sort of standard C++ code. It's more about the abstraction of where things have to live that you get into trouble. So just to sort of cover my bases, I also wanted to mention, there's a lot of options for GPU programming these days. Cholla is written in CUDA. That's partly because at the time when we started writing it, CUDA was, by far the most mature programming API. It was developed by NVIDIA for their GPUs. It supports C++ and Fortran. It still often provides the fastest execution for a lot of problems. And it has a lot of libraries and third-party support. That said, of course, the downside of CUDA is that it is NVIDIA's proprietary language. And that means that you're sort of tied to using NVIDIA's GPUs, and it's not an open software, which is not so appealing. There are a lot of other options these days. AMD has HIP, which is basically the same as CUDA, right? It's just AMD's version of that programming API. And then there are a bunch of open platform, cross-vendor options, including OpenCL, OpenACC, which I say, with a sort of asterisk is vendor neutral, because actually NVIDIA started, sort of leading the development of OpenACC a few years ago. So it's more targeted at this point towards NVIDIA GPUs, and OpenMP sort of similarly is more targeted towards, Intel. So, for any given problem, which of these models is the best to use in some part depends on, what system you think you're going to run on. More recently, there have actually been some new options that I think are going to be the way forward. These are sort of, the performance portable programming models. And I mention them because they're designed for actually sort of heterogeneous compilation. You can either compile for CPU-based parallelism or for GPU-based parallelism across a lot of different platforms. So, Kokos and Raja are two examples of this that are being developed by national labs. Both of them basically, intend to ideally become part of the standard C++ API. So the sort of parallelism will be built in to a future version of C++. There's also SYCL, which I think, is developed more by Intel and developed with the intent originally of sort of running on Intel's sort of parallel processors, but is now also compatible with sort of vendor neutral GPUs. So I think these are probably the way forward, and that's part of the reason I wanted to mention them, even though I'm mostly talking about programming that we've done using CUDA. So to just dig in a little bit to how this actually works, I'm going to talk a little bit about a project that we spent the last few years doing, which is to say, Cholla was originally developed, starting in 2013, 2014. And the way that we developed it then, which worked quite well, we've had to update and modify quite a bit in the last few years. So we did this as part of a project sort of sponsored by Oak Ridge National Lab in order to kind of get ready to run on Frontier. And so a lot of what I'm going to talk about in the next few slides basically has to do with, what were the modifications that we realized we needed to make to be able to run more efficiently on a sort of modern GPU supercomputer. And so at base, right, Cholla takes your simulation domain, which can be quite large, right, and divides it up into subvolumes. And we use MPI to deal with multi-node communication, right? So we assign a bunch of MPI ranks to each of these subvolumes. Cholla is a static mesh code, so the domain decomposition is simple, and each MPI rank is given a single GPU. So each GPU is responsible for a subvolume that's a typical size might be 128 cube cells, or these days maybe 256 cube cells, and then each cell, as I said, is mapped to a sort of single thread GPU, right? And back then, we had the ability to sort of further subdivide volumes if the data didn't fit on the GPU. This was important because I'm starting to feel old, but when I started developing Cholla, I was developing on a GPU that had like 2 gigabytes of global memory, and so this was a problem. You couldn't really fit a reasonable problem size on the GPU. Now this is less of an issue. A typical HPC GPU has 60 gigabytes of memory or more. So we no longer have to do this sort of subdividing, and you can just, sort of put everything on the GPU. Similarly, right, Cholla is not actually just a hydrodynamics code anymore. It has a bunch of additional physics modules, so we can run cosmological simulations, radiative hydro, that kind of thing. A lot of these were added by Bruno at UC Santa Cruz as part of his thesis. But this was a bit of a problem when we started this project to run on Frontier, because the hydro was running totally on the GPU, but some of the other physics modules weren't. So in particular, the gravity, which we do using FFTs, which we were using, FFTW for at the time, was done totally on the CPU. This was partly because we wanted to sort of overlap the gravity compute and the hydro compute to get, more parallelism out. And partly because we didn't have a good FFT decomposition for the GPU, as I'll talk a little bit more about in a couple of slides. But the idea was that fundamentally the simulation data kind of lived on the CPU, and then you transferred it to the GPU for like heavy compute applications like the hydro module. and then transferred it back each time step, and sent your boundary data around, just using sort of standard MPI calls from the CPU side. And this was not going to work for Frontier for a variety of reasons. In particular, this is kind of the offloading model of GPU programming, where you have a bunch of stuff that's kind of sitting on the CPU in your program, and then when you have a heavy compute problem to do, you send the data over the GPU, do the computations, and send it back. And we needed that in the beginning, again, partially just because the GPU memory wasn't big enough. But GPU speeds have gotten way faster in the last 10 years, and they're still getting faster. Whereas the sort of CPU GPU communication speeds have lagged behind, right? I mean, we are on PCI Gen 5 or whatever now, but the increase in speed on the communication side has not at all kept up with the increase in compute speed. And so we were at the point where this data transfer was taking up, more of a typical time step than the actual hydrodynamics calculation, which is supposed to be, pretty heavy. So the solution to this was going to be to keep all of the data on the GPU, right? Just have GPU resident grids for everything, the hydro, the gravity, et cetera. And also to take advantage of, now we have GPU aware MPI calls. So we can just transfer from, GPU to GPU buffer directly using MPI, and only transfer data back to the CPU if we need to output. And that algorithmic change alone resulted in about a factor of 4 speed up for us, just for, for example, for the hydro module, which was already quite optimized on the GPU itself. We also had a problem in that, I mentioned that Cholla was written in CUDA, which is, for NVIDIA GPUs, but Frontier and, several other leadership class supercomputers these days use AMD GPUs. AMD uses HIP, which again is an API that's extremely similar to CUDA. But you can't compile CUDA code for AMD GPUs. So one option that we had that AMD sort of favors is just to rewrite all of your source code, basically swapping out all of the CUDA functions for HIP functions, and then their compiler HIPCC will compile that code for either NVIDIA or AMD hardware. We didn't love that option because then even if you were working on a cluster that only had NVIDIA GPUs, you would need HIP to compile it, which maybe wouldn't be installed because why would it be? We actually came up with a sort of lighter weight portability solution, which we call Hipifly, right? Which is hip on the fly, where basically we just added a single header file to the code that redefines all of the CUDA calls as HIP calls, and this header file gets compiled if you're compiling for an AMD hardware. So this was pretty straightforward, and again, I mention it in case anyone here is thinking about they have CUDA code and they want to port it, or want to see an example of how this could be done. Because CUDA is still nice in that it is still the most mature of the sort of GPU programming languages, and it has a lot of features. So this gives us a sort of single performance portable code base for either sort of AMD or NVIDIA GPUs, which are the sort of dominant GPUs on these computers. I'll mention in the last couple of minutes the sort of third challenge we had. So I mentioned earlier that our gravity solver, our Poisson solve, is an FFT-based solve. Our domain decomposition is block-based, and that meant that we needed a sort of block-based FFT library to do the Poisson solve. And when we were doing this on the CPU, we used a library called PFFT, which then uses FFTW. But there wasn't really an existing parallel block-based FFT library for GPUs. So one of the members of our team, Trey White, who was working for HPE and now works for Oak Ridge, wrote a new block-based Poisson solver called Paris that can use either NVIDIA's cuFFT library or AMD's RockFFT library to perform all the FFTs on the GPU, and uses GPU direct MPI communication to transfer information off node. And this again resulted in something like a 4 times speed up for our gravity module compared to doing things on the CPU side, even though you still have a lot of communications. So again, I mentioned this in part in case anybody is has a similar problem or is looking for a sort of FFT based Poisson solver, and this is all also available on on GitHub. So Trey has just a standalone benchmark version of Paris in case anyone is interested in that. All right, so to kind of wrap up, right, what does this mean about how this works today? Basically, the idea is we keep everything resident on the GPU, right? The grid data lives there. We have our sort of time step loop where we can run through all of the different modules, all of which are, taking advantage of the GPU hardware. In the end, this means that the code, even when running with all of these different physics modules, as on the same hardware, like if we run on, Summit, we're about 4 times faster than we were before we made these improvements. Yeah, Michael's saying, have we thought about multigrid? Yes, we have thought about multigrid, and it's on our sort of to-do list. I think on small scales, FFTs are probably faster, but on large scales, because of the communication, yeah, it might make sense to do multigrid. So anyway, just to add a couple more things that are nice about having this new sort of data structure on Frontier and on increasingly on new GPU enabled supercomputers. The GPUs themselves have data links to the network. So, the GPUs can just talk to each other through the network without having to pass anything over the CPU side. So that also is something that we can now take advantage of using this sort of, GPU aware MPI, and then passing things directly from the GPU
Evan,
buffers.
sorry to interrupt. Have about 2 minutes left, maybe.
Yeah, I was going to say, this is my second to last slide. So just to kind of wrap it up, right? This is the sort of end of this effort. Right, on Frontier, we have these network connected GPUs. We have faster hardware, and so just by making these sort of algorithmic improvements, we're about able to do problems that are about 20 times larger than what we could do on Summit about 4 years ago. So that's it. I just wanted to kind of highlight some of the things that we were thinking about in terms of trying to improve an already GPU native code. So that's my last slide.
Thank you, Evan. Yeah, this was very interesting. I think you kind of answered one of Mike's questions during the talk. So maybe we'll just move on to Ben, and then if we have time for other questions in the open discussion section, we can ask them then, if that's okay.
Sounds good.
Okay. All right. So yeah, next is Ben Wibking from Michigan State, and he's going to talk about Quokka.
Great, thank you so much. Yes. Let me start my slides. Does that work?
Yep, looks good.
Okay. Are you seeing the slide view?
No, it's the right
What we
thing.
should see. Yeah.
Oh, okay. Okay, great. So yeah, I'm going to talk about Quokka, a new code for AMR on GPUs and all the fun stuff we encountered trying to do that. So yeah, as Evan said, GPUs, I'm going to motivate this in a very similar way, which is that starting with Moore's law, which is an observation the number of transistors in an integrated circuit doubles about every 2 years from Wikipedia. But in practice, people have expected this to mean that computer performance will double every 18 to 24 months at fixed costs. And the amazing thing is that for decades, this was basically true. So here's a slide showing the transistors per chip, which is sort of the most direct thing that Moore's law would say. It's been increasing exponentially at a constant rate since the 1970s. Beautiful, but clock speed has not. So the actual speed of a single processor hasn't increased. So initially people did, in the 1990s, most astrophysics codes didn't even use MPI, which is amazing to think about. But that was sort of the era of my PhD advisor, and his pioneering simulations were 32 cubed and ran on a single processor. I wish I could do that today. But as we move toward bigger and bigger simulations, computers unfortunately stopped getting faster for free, and their power consumption also kept increasing. So I have this funny picture of the CEO of NVIDIA where he says, Moore's law is dead. The ability for Moore's law to deliver twice the performance at the same cost, or the same performance at half the cost every year and a half is over. So this has made him very wealthy, but I think it's also true. So simulations are crucial for astrophysics in a lot of ways, but the free lunch of just things getting faster for free is over by waiting for the next computer every year, every other year. So what do? We go to GPUs because GPUs are basically on a trend line that's like an order of magnitude higher than the CPU trend line of performance. So Quokka. Quokka is an Australian marsupial. It's found basically only in, or it's mostly found on a single island off the southwest corner of Australia. So I've never actually seen one in person, even though I did my previous postdoc in Australia. I was entirely on the east coast of Australia, but the quokkas only live on the southwest coast. And I think marsupials are appropriate because they carry their young in pouches, which is sort of like how AMR works on a very loosely analogous level. So the science motivation for writing this code was to simulate star clusters. So here's the star cluster simulation that I did with Quokka. So it's very simple. So there's actually there's no star particles. There's no actual star particles here, but there's gravity and hydrodynamics and turbulence that forms. So this was the basic motivation, and there are multiple levels of AMR in this calculation, which you have to have basically to follow structure as it collapses over, from a parsec scale basically down to an AU scale. In a star cluster. So that's 5 orders of magnitude of dynamic range that you have to follow in this sort of calculation. And the equations you have to solve are the equations of radiation hydrodynamics, which are the first 3 are the equations of hydrodynamics that Evan talked about. But we also have to solve 2 additional equations, but one additional scalar equation and one additional vector equation, one for the radiation energy density and one for the radiation flux. And we actually have to solve more equations than that because we have to solve these 2 equations of radiation transport for every energy group that we care about, every range of photon frequencies that we care about. And so the traditional method to do this has been to use implicit methods, but those don't scale very well. So we wanted to use a more scalable method. And so the solution that people have proposed that the community has moved toward is basically this reduced speed of light approximation, where you have the normal speed of light, which is moving as fast as the hair, but it's 10 to the 5 kilometers per second. But a typical gas velocity in a molecular cloud is like 1 kilometer per second. So we artificially reduce the speed of light to maybe 100 times the maximum gas velocity in order to be able to simulate the full system with an explicit in time Runge-Kutta method, while having sort of hopefully a minimal impact on the dynamics. Although it's not always true, but it's mostly true for the problems we care about. So as I said, the solution people have proposed is to use the reduced speed of light approximation. It maintains a qualitatively correct solution in a large part of the parameter space. It's more scalable than implicit methods, and it turns out it's better suited to GPUs because the memory accesses are more regular, which is very important for this property of the GPU hardware known as memory coalescing, where you basically have to access a whole cache line in memory at once. All of the GPU threads, send out requests to access all of the bytes in memory that they want, and then the hardware coalesces it into the minimum number of cache lines it has to fetch from the main memory. And this is the number of cache lines it has to fetch is reduced if all of the memory is contiguous, or all of the requests from all of the threads are contiguous in memory. And so with implicit methods, you have a sparse matrix and you're accessing sort of data essentially randomly, and that doesn't happen. But with this explicit method, just like in hydrodynamics, you're accessing data in a way that is more or less contiguous in memory across all of the threads. And then, so to implement this, we have these very complicated source terms between coupling the radiation and hydrodynamics that we take from the Bible, also known as The Foundations of Radiation Hydrodynamics by Mihalis and Mihalis. And this shows that this is actually the simplified form of the equation. The current version of the code has even more terms, has some terms up to v squared over c squared, which turns out to be necessary in the dynamic diffusion limit. But yeah, so there are these complicated coupling terms that differ in different regimes. And that turns out to be a complicated physics piece, but doesn't add any additional complication to the GPU programming itself. And so we followed sort of what the rest of the galaxy and star formation community has done and adopted this M1 closure, which basically assumes, so when you simulate the equations of radiation hydrodynamics, you have to have some closure for the radiation pressure tensor. And here we have a local closure for the radiation pressure tensor in terms of the radiation energy density and the radiation flux. And so this ends up giving you the right solution in the free streaming limit and in the asymptotic diffusion limit. But doesn't get things right in between because you need some non-local information. But it's the best you can do without computing a formal solution to the Boltzmann equation. So we didn't want to do that. So we're doing at least as good as most of the other codes for now. So what is AMR? So now we're getting to new stuff. Basically, the kind of AMR we do is like the Quokka. We have a refined region, which is sort of the baby Quokka, placed on top of the parent grids, which is the parent Quokka. But unlike the Quokka, the parent and child grids don't actually have to have a single parent. They can have multiple parents. Well, actually, that's not true of Quokkas, but there can be an arbitrary number of parents for the AMR grids, whereas that's not true for Quokkas. And so the physics reason is that we have a lot of, a huge dynamic range of structure, but also we want to resolve sharp gradients in the solution. So previous work in star clusters has shown that refinement on optical depth gradients can change the answer qualitatively. So if you refine, for instance, only on the gene's length, you get the solution on the left. And then if you refine additionally on the optical depth gradient or the radiation energy gradient in practice, in this case, you get almost a totally different, you get a very different solution that affects the instability around the bubble blown around this star by radiation. So for the physics questions we're interested in, we basically have to have AMR for our problems. But it turns out there are a lot of different kinds of AMR, and people don't always sometimes think you're talking about the same thing, but you can actually be talking about a type of AMR that's totally different. So in terms of patch-based AMR, there are basically two different kinds, the kind on the left and the kind on the right. So the patch-based AMR we use is the kind on the left, where the grids can have an arbitrary size and can have almost arbitrary placement with respect to their parent grids. But some AMR codes like Flash and ENSO-E and Athena++ and Gamer require a strict hierarchical decomposition. So this has every grid is the same size in terms of number of cells and is only refined in octants or 1/8 of a cube of the simulation domain. So yeah, for our type of AMR, the grid sizes can differ. The child grid doesn't have to have a single unique parent, and the time step can also be different for different grids. And this is the type of AMR used by Castro, Orion, ENSO, and a few other codes. One difference with ENSO is ENSO requires each grid to only have a single parent, whereas we don't require that. So I guess many codes in the astrophysics codes for simulating stars and galaxies use particles or unstructured meshes like a repo or gadget. But this turns out to be a poor fit for GPUs. So as I mentioned before, structured grids are well suited for GPUs because they have predictable memory accesses that allows the hardware to perform memory coalescing without fetching unnecessary bytes from memory. And then you get a high effective memory bandwidth, which turns out to be the limiting factor for performance for Hydra codes, for basically all Hydra codes. And we also avoid individual particle time steps. So codes like gadget and a repo, typically every particle can have its own time step. But this means that only a few dozen or a few hundred particles per MPI rank are advanced on any given time step. And so there's not actually enough parallelism to saturate the GPU. So as Evan mentioned, you need to have basically millions of work items, millions of cells to work on for the GPU to be efficient and to actually be faster, significantly faster than CPUs. So there's really not enough parallelism for codes that use individual particle time steps. There are particle codes that use a global time step for all particles, where they've completely rewritten their algorithms to work. But again, they use a global time step for all particles, which is not practical for high dynamic range problems with gravitational collapse, where you have to follow things over many time scales and length scales. But basically, the conclusion is gadget-like SPH codes can't run efficiently on GPUs. And it's really a fundamental issue with the nature of the algorithm, not the quality of the implementation. I actually spent my undergraduate thesis trying to get gadget to work on GPUs, and it worked, but it was just slow. It was never faster on all of the GPUs on a node compared to all of the CPUs on a node. And no one has really found a way to make it work efficiently on GPUs. And it's really a fundamental reason due to the nature of the algorithm. So to work on GPUs, I would say you have to choose the right algorithm, or you have to choose an algorithm that has sufficient parallelism to have millions of threads on all of those hundreds of GPU cores. So what we did, we took a pretty different approach as compared to Cholla. So we, as I sort of paraphrasing Newton here, we're building on the shoulders of giants. We're using the AMRX library, which is funded by the US Department of Energy for all kinds of different AMR applications as the foundation for our code. So we wrote it in Scratch in C++, and we use AMRX to do all of the communication and grid management, grid generation, and also AMRX handles the GPU interface. So it has a C++ Lambda function based GPU abstraction, which turns out to actually be very similar to Quokka's, but it's specialized to the grids and data structures used in AMRX. So it's less general, but more efficient for our problems and simpler for users to use. So I'll show an example of what that looks like. So essentially the same code Evan showed for the time integration, taking the fluxes around each cell and integrating them in time. We just call this AMRX parallel 4 function, which takes a range of grid indices, and then a C++ Lambda function, which is this very strange, if you haven't seen before, is this thing with sort of strange syntax that begins with the equal sign, the AMRX GPU device, preprocessor definition, and then it takes the grid indices and then a function that operates on those indices. So this is how we program all of our GPU kernels. It works really well. It's basically as fast as writing it in native CUDA, but it's also portable because we can just recompile it for HIP, or we can recompile it for SYCL. Actually, we currently can't recompile it for SYCL because the SYCL programming model doesn't support function pointers, which we need for our code. But in principle, you can just change the compile time parameters, recompile it, and it works for a different GPU architecture as long as AMRX supports that GPU architecture. So yeah, one of the motivations is to run on the biggest GPU machines, like Evan mentioned. Frontier is the biggest machine, has almost 40,000 GPUs. It costs $600 million. So it'd be great if we could run on this machine. And that was a big motivation to run on sort of, not only Frontier, but basically all of the next generation state-of-the-art high-performance computers have GPUs, as Evan mentioned. So what is the performance benefit? Well, sort of the bottom line performance benefit is that on a node-to-node basis, running on all the GPUs versus running on all the CPUs of a node, typical GPU node, it runs about an order of magnitude faster, typically like 10 to 13 times faster, running on GPUs. And it scales almost perfectly in terms of weak scaling. So we get about 88% weak scaling efficiency, going from a single GPU node to, in this case, a few dozen GPU nodes, but we've actually continued our scaling studies out to several thousand GPU nodes on Frontier. And we get essentially the same scaling efficiency, just under almost 90% weak scaling efficiency to thousands of GPUs. And there's sort of a plot comparing it to other codes. So yeah, this shows the speed up we have compared to Athena++. Athena++ is slightly faster on CPUs because they do some very CPU specific optimizations that no one else can seem to quite beat, but it doesn't make it general and basically prevents Athena++, the loops from working directly in a performance portable way. So I would say Quokka's unique capabilities are it can run efficiently on GPUs. Well, that's not unique, but for codes that can handle a high dynamic range problem, can run efficiently on GPUs when compared to particle-based simulation codes. And that's essential for running on exascale supercomputers. And it can take different time steps on each resolution level. So it doesn't take different time steps for each cell or for each grid. But for each resolution level, all grids at the same resolution take a given time step, which can be different from grids at different resolution levels. And so that turns out to also be essential to run efficiently high dynamic range problems with 10 or 20 AMR levels. So I think the maximum number of levels we've run on is like 21 AMR levels for a star formation problem. And yeah, so that turns out to be very useful for those kinds of problems. And yeah, so we've added a bunch of other physics, and my collaborators in Mark Krumholtz's group have added other physics, such as chemistry, particles, and magnetic fields. Magnetic field capability is currently in development. We do gravity using the AMRX multigrid, built-in multigrid solver instead of FFTs. So it scales really well. It still takes up a lot of time. So our simulations with gravity, still 50% of the wall time, more or less, is spent in the gravity solver. But it scales very well, and we're pretty happy with the built-in multigrid that we have, and it allows us to do to solve the gravity consistently over different AMR levels. So I'll leave you with this simulation I did of cloud crushing. And so this is a simulation I ran on GPUs, and you can see, all of the small scale Kelvin-Helmholtz instabilities forming. Whoops, I didn't mean to exit out of that in the simulation. And yeah, I think this is a simulation that really would not be feasible to do a large number of these on CPUs. So we're, I think, just at the point of getting to new science that couldn't have been done without GPUs. I think it's really cool. So I'll be happy to take any questions that you have.
Awesome. Thanks, Ben. That was great. Does anyone have any one quick question for Ben before we open the open discussion section?
I think you had one, Sam.
I do have one, but if somebody else had one, I was going to let them go. But okay, so yeah, I was curious. You mentioned that the time step is different for each refinement level. How was that time step determined? I think you're muted.
Yeah, so we first determined the maximum signal speed over all cells, over all levels, and perform an MPI reduction. Yeah, so that's basically, the absolute value of the fluid velocity plus the sound speed, and then compute that the maximum over all cells. And then we use whatever our CFL number is to set the time step on each level, because then the time step on each level just differs by whatever the delta X is, whatever the resolution is on any given level. I think that's pretty much the standard way to do it for this type of AMR.
Okay, that makes sense. Thanks. Okay, well, yeah, so I guess for the next 5 minutes or so, we can have open discussion. So if anyone has any questions that they have, I don't see. Oh, let's see. There's one that Brian put in the chat.
Just
So,
ask it.
sure.
So yeah, so this was directed at you, Evan, since you've done a lot of performance testing on a couple of different architectures, and I was curious about if you saw, like, if the same looping structure when you used your HIPAA tool, like, does the same looping structure give you like noticeably different performance on NVIDIA versus AMD GPUs? Because the actual structure of the hardware is different, so I wouldn't necessarily bank on it being the same.
Yeah, so I guess, first I just want to make sure we don't really have a looping structure. And so I might have confused people by showing the sort of CPU version of the kernel first, but the HIPAA version of the code is virtually identical to the CUDA version, just with all of the CUDAs changed to HIPs. Like, HIP is really just a sort of copy of CUDA, right? They would not like to hear me say that, but it's true. And so actually but to answer your question, we do see differences in performance that I think are actually more based on the fact that CUDA is just a slightly more mature language, and the MBCC compiler is a more mature compiler. So for reasons that I don't 100% understand, like, NBCC does a better job of reducing the number of registers for a given kernel, right? And since, again, memory bandwidth and memory pressure are typically our biggest, limiting factor, that seems to make a difference. And so on the sort of equivalent, generation hardware, we're always faster on the NVIDIA GPUs, even though in principle the APIs are so similar that they should be doing very similar things. I don't know if that answers your question, but.
It does, yeah. I guess what drove me to ask that was when a few years back, we wrote a paper where we were with our experiments using Cocos on Athena++, and we ended up writing these macros for Cocos that would let us like give Cocos varying amounts of instructions for the same compute kernel. So you could tell it, just treat it like a big 1D loop, treat it like, a variety of different things like slabs, threads, all sorts of things, and saw like really wild performance differences between those. And so that was the basis of that was the origin of my question.
Gotcha. Yeah. No, so so it's the same memory access structure. It's the same. Yeah, everything's the same between the two. But we do typically see better performance on the NVIDIA.
Okay. And that's pretty well aligned with what we've seen too. Thank you.
I had one question for both of you. I was just curious how many developers do each of you have for your codes? Maybe Evan first, and then second.
Well, it kind of depends. Yeah. So I mentioned that we were part of this project, the Center for Accelerated Application Readiness project, which was kind of hosted jointly by Oak Ridge and like the sort of exascale computing project. So at that point, like, there were, maybe 10 active developers. We had to get a lot better about like managing our GitHub repo and that kind of thing. I think, more typically these days, it's 5 or 6 in the sense that, that's kind of the number of students and postdocs and so yeah, but that's, a dozen sort of max at one time.
Okay.
If I can piggyback on that, Evan, what's your experience been as, relatively new faculty in getting new students up and being comfortable with making contributions to your code?
It's better now that we have a sort of good integrated testing system. But also, I mean, something that I still struggle with, as you say, as new faculty, is that it's so wildly different from student to student, even if I take the same approach. So all of the students who I've worked with so far, are able to sort of get up and running and start making like modifications to the code that they push to the repository like within 6 months. But that is partly because now we have a structure where we do kind of try to like identify low level issues, right? And we have hack days where then they can work on something that's in principle really simple, right? And then run the tests to make sure that nothing's broken. Whereas like some of the more heavy duty lifting, it's still not clear to me like the trade-off between getting students like really digging into the code versus the sort of time that it takes to ramp up versus kind of like giving them quick and dirty projects and that kind of thing. So I don't know if that's
No, yeah, I understand what you're saying.
So quick, Ben, if you could, I was curious how many people work on your code, and then Tom has his hand raised, and then but it is noon, so if people need to go, obviously, please feel free to leave whenever you want.
Yeah, so I just looked at our GitHub contributor list, and we've had 6 students and postdocs, including myself, contribute to the GitHub repo so far. Yeah, so pretty small. No one outside my current and former groups has used it yet, but always happy for new users and developers, if anyone is interested.
Okay, cool. Thank you. And then Tom has his hand raised.
This question's for Ben. So when you said level 21, this is exactly in ENSO where we had to go to quadruple precision because we sort of ran out of precision to represent the coordinates and also the time steps. So I wondered whether you think that's the same issue in AMREX, or whether there is an easy way to just use the hierarchical nature of the grids to infer and actually calculate where you are instead of explicitly keeping the coordinates and delta x's.
Yeah, so we haven't used quadruple precision. We haven't had to use it. The thing we run into that limits the number of levels is actually that so each grid is we only have 7 integers per grid in terms of metadata in AMRX, which a lot less than ENSO. So I don't know if that's part of the source of the issue, but we store the global coordinates on each level in terms of the X or the IJK starting index and ending index, and then an integer for the type of grid, whether it's cell-centered or face-centered or node-centered, and that's it. So, but these are currently
those integers on a
unsigned
global
integers.
Grid or on the parent grid?
Integers on the global grid. Yeah,
So
the
it's the
virtual
global grid.
coordinate, the virtual
Okay.
global grid. Yeah.
All right.
So the thing that limits that is the fact that we
issue then.
use 32-bit integer for those integer coordinates.
Okay.
So we
Thanks.
can't have more than 2 to the 31 virtual cells per level.
Thanks.
Yeah.
Well, thank you, everyone. It's past noon, so probably time to end. But yeah, thank you again to Ben and Evan for presentations. They're both excellent, and now I understand how to pronounce the names of both codes, so that's always good. And yeah, and thanks everyone else for joining. And we'll have another VAST next month. It'll be on October 16th. So
And they're sort of machine learning topics.
that's okay, yeah. And then if you have any students or anyone that you think would like to give a talk, then please urge them to submit a GitHub issue with our page, and yeah, we can try to get them scheduled in. So yeah, thanks everybody, and we'll see you next time.
Thanks, Evan and
Thank
Ben.
you.
Those are both great talks.
Thanks for having
Thanks.
us.
Take care.